In this video, I'm going to talk a little bit about points on angle bisectors. But before that, I want to at least make sure we understand what we mean when we talk about the distance between a point and a line. So let's say that that is some point, point A, and this is some line right over here. We'll call that line BC. So when you're taking the distance between a point and another point, it's very obvious. You just draw a line to that other point. Well, I already used B. You just draw a line to that other point, and you find the length of that line. So distance seems very straightforward between 2 points. But what about a point and a line? Because there are many points on this line. So maybe we're going to find this distance, or maybe we're going to find this distance, or maybe we're going to find this distance. And these are all going to be different lengths. So how do we have one unique distance? And the way that we think about this, and we're going to do this in much more depth in future math courses, especially once you study vectors and linear algebra and all the rest, is a distance between a point and a line is really the shortest distance. And that shortest distance is if you were to drop a perpendicular from that point to the line. So this right over here is what we call the distance between the point and the line. And this is perpendicular right over here. And to recognize that this is indeed the shortest distance, think about this relative to the distance between this point and any other point on this line. So pick another point on this line right over here. Let's call this point E. And let's think about this distance. Now, this is an arbitrary point. I could have drawn E here. I could have drawn E here. I could have drawn E anywhere. But regardless of where you draw E, if you draw a line segment between A and E, you see that we form a right triangle from A to E to the point where we had the perpendicular. So let me call this point right here F. You're always going to draw a right triangle, assuming that E is different than F. And if you do that, you'll immediately see that D has to be shorter than this orange length, because this orange length is a hypotenuse. The hypotenuse is always going to be the longest side of a triangle. D squared plus whatever length this squared is going to be equal to this length squared. So hopefully that at least gives you a decent sense why dropping the perpendicular will always give you the shortest distance between a point and a line. And that unique shortest distance is what we call the distance between a point and a line. Now, with that out of the way, let's think a little bit about angle bisectors. So let me draw an angle here. So let me draw an angle. So let's call this point, we do it in different colors. Let's call that point A. Let's call this point B. And let's call this point C right over here. And an angle bisector is essentially a line or segment or a ray that splits an angle into two equal angles. And we've talked about this a little bit before. So for example, if we want to bisect angle ABC, so this angle right over here, we want to split it in two. We are going to split it in, I can actually draw a better version of that. We want to split it in two. We want to split it into like, let me draw a little bit better. The drawing is, no, that still doesn't look like, that looks decent. All right. And so let's call this point right over here, I don't know, let's call this D, and maybe we could even say that's an array, or we could call that a segment, or whatever. But the way to think about this is if now angle DBC is equal to angle DBA, so if this angle DBC is equal to angle DBA, we can say that DB bisects angle ABC. So we could say that DB, and now I'm talking about segment DB. We could have made it array if we made it keep going to the right, or a line. DB bisects angle ABC. ABC. Fair enough. Now, the whole reason why I started this video talking about distances between points and lines is that I want to show you that any point that is on an angle bisector is actually going to be equidistant from the sides of the angle. And then we're going to go the other way to show that any point that is equidistant from the sides of an angle is going to be on the angle bisector. So let's take an arbitrary point that sits on this angle bisector. So let's take this point right over here. I'll call that arbitrary point F. Or actually, I could use E. I haven't used E yet. So this is going to be an arbitrary point on our angle bisector. And now let's look at the distance between E and BC and the distance between E and BA. We already said that the distance between a point and a line is if you drop a perpendicular from a point to that line, which you can always do. So let's draw a perpendicular right over here. This is one distance, and then this is the other distance. This orange line right here is the distance between E and BC. This is the distance between, and this orange line is the distance between E and BA. And what I want to prove is that these distances are equal. Well, the first thing to realize is that we have two right triangles over here. They both have this same angle. They're not sharing it, but angle angle ABE is congruent to angle CBE, and we know that because DB bisects it, so this angle is equal to that angle. They're both right triangles, so they actually have two angles in common, which actually means that they actually have three angles in common. It constrains what this other angle would be. And they also have this side in common. And when I say they have three angles that are congruent to each other, they're not necessarily in common, but it does have this side in common. BE is the hypotenuse of both of these right triangles. And so you can invoke, using this angle, and this side, this angle, that angle, and this side, you could say that these two triangles are going to be congruent to each other. So we could say that triangle, and let me put some points over here. So let's see, let's call this F, and let's call this G. We can say that triangle EBF is congruent to triangle EBG, and we could use it angle side by angle side congruency. Or you say, hey, if two corresponding angles are the same, then that third angle is also going to be the same. So this angle right over here could also be the same. And then you could use angle side angle. But either way, these two things are going to be congruent. But if these two things are congruent, then the corresponding sides are going to be congruent. So then length of EF, segment EF, is going to be congruent to segment EF is going to be congruent to segment EG, which is the same thing as the length of EF is equal to the length of EG. These are really equivalent statements right over there. So the length of EF is equal to the length of EG, and the length of those two segments are the distances between the point and those two respective sides. So we've just proven the first case. If a point lies on an angle bisector, it is equidistant from the two sides of the angle. Now let's go the other way around. Let's say that I have, so let me draw another angle here. So let me draw another angle right over here, and let's call this A, B, and C. And let's pick some arbitrary point E. Let's pick some arbitrary point E right over here. And let's say we start off with the assumption that E is equidistant to BC and BA. And what we want to do is prove that E must be on the angle bisector. So here, if you're on the angle bisector, you're equidistant. Over here, we're going to show if you're equidistant, you're on the angle bisector. So if it's equidistant to BC and BA, then this perpendicular right over here, is going to be congruent to this perpendicular right over there. And let me give these points labels. So let's call this point D, and let's call this point right over here F. And let's just draw segment BE here. Let's just draw segment BE right over here. So once again, we have two right triangles. We already know that two of the legs are congruent to each other. They both share the hypotenuse. This hypotenuse is equal to itself. We know from the Pythagorean theorem, if you know two sides of a right triangle, it determines the third side. So, and we know two sides of both of these, so their third sides must be the same. So this side must be equal to that side. So you could invoke SSS, side, to show that these two triangles are congruent. Or you actually didn't even have to go there. You could have used a special case, the RSH case, where if you have a right triangle, so if you have the right triangle, you have one set of sides that are congruent, and you have the hypotenuse that is congruent, then you're also okay. You could use RSH to prove congruency as well. And so either way, we know that triangle EBD, is congruent to triangle EBF. It's congruent to triangle EBF. We used side here, but you could have used RSH. Let me write that, RSH. which is, we know that angle side-side can't be used for any general triangle, but it can be, RSH is essentially angle side-side for right triangles. If you have two sides of a right triangle and if you have two sides of a right triangle in common, then if two sides of a right triangle are congruent, then the two triangles are definitely congruent, which is what essentially this is saying. But once you know that two triangles are congruent, then their corresponding angles have to be congruent. And angle EBD corresponds to angle EBF. So we know that angle EBD must be congruent to angle EBF. So EBD must be congruent to EBF. Well, if EBD is congruent to EBF, then that means that segment EB, must bisect angle CBF, or I should say CBA even. It could be called CBF. Angle CBA. So we're done. If over here we showed that if something sits on a bisector, is equidistant from the sides of the angle, and here we showed if it's equidistant from the sides of the angle, it sits on the angle bisector, or it could even be the endpoint of an angle bisector, but clearly it sits on it.